Thank you for inviting me to this nice conference, Thomas. And it's a great pleasure to talk with about some work we have been doing with a number of, different people here. Some of the talks you're hearing about it, for example, over I would say in the past 20 years, but with more effort in the past 5-10 years. So it's increasing activity in these directions. The aim of this talk is towards mathematicians. So sorry if it's just not for you guys. And so therefore, this is going to open up, hopefully, feeling that you can ask any questions you want. It's not supposed to be clear to mathematicians, okay? I will try my best to convey what we are doing, and therefore you should ask questions, a very informal talk. I'm not trying to prove anything. I'm not going to even define anything. So I'm going to just give you some aspects of what we are doing in physics. So we should take the viewpoint of not, very precisely defined things, but this collection of ideas that are emerging as important in physics that hopefully will connect to the more mathematical areas that we heard, for example, today and yesterday. And so hopefully we will have some commonality, because I do feel that there seems to be a common trend in this direction with what we are doing, but we still haven't figured out exactly what. And that's part of it is, instead of giving a very detailed description of what we're doing, a higher level of generalities might be more useful at this stage. So I apologize for a lot of generalities, because that's all I think is the more useful one right now. But I hope that math colleagues here will ask me questions. It's very informal, so don't feel like there's anything specifically you have to know about anything specific, so physics-wise. So feel free to ask any questions. Okay, so with having said that, let me just say the basic motivation for the Swampland program is having to understand the distinctions of what we call quantum field theories versus quantum gravity. So these are two different topics in physics. The quantum gravity could potentially be viewed as a subspace of this guy, but quantum gravity specifically includes gravity in it. But quantum field theory generally does not need to have gravity in it. We don't need gravity a priori. What does it mean? It means, in terms of physics, that metric of the manifold that you're interested in, we are living in or describing the physical process, is dynamical, which means that you have to allow it to fluctuate and do that stuff. That's quantum gravity. Whereas if you freeze it, like flat space or any fixed geometry, which you're not allowed to change, frozen background, that gives you what we call quantum field theory in those contexts. This turns out to be that these distinctions turns out to be a big difference between the two theories. Possibilities are very different, just whether or not you allow the metrics to vary or not. Freezing metric or not freezing metric. Okay. I would say, in a sense, these are well understood. Quantum field theories without gravity, not necessarily from a mathematical standard, but from a physics standard, we would say we have understood them. Understood them in the sense that we know what are the allowed choices we can make, what is the class of quantum field theory, especially in 4 and lower dimensions. We have a good sense of what are consistent good theories. And needless to say, they are very complicated in general. There are infinitely many of them, and so forth. This depends on what kind of bundles we consider dynamical, what kind of representations of those bundles we allow in your theory, and so forth. But we know exactly what are the choices, and there are infinitely many choices, depending on choice of your gauge bundle, choices of what kind of sections we allow, and what representations they go, and so forth. So that's the basic part. And then quantum, the word quantum here would basically relate to the fact that they would be dynamical. Namely, you don't freeze the connection, you don't freeze the sections, you vary them. You allow them to be dynamical, as opposed to here, which you also, in addition to those, you also allow the metric to also vary, not fixed frozen metric. So that's just the basic difference between these two subjects. Now, ordinary techniques in century-old techniques in quantum physics has led to big progress on this side. We can talk about things like Feynman diagrams to give you a perturbative scheme when you have small parameters in your theory and so on. So we can deal with some schemes of calculation here in some asymptotic expansion of your amplitudes in various regimes. And so we have basically a good understanding, I would say, for both perturbative aspects of it and what we expect, even away from weak coupling in some general terms. For example, confinement, some strong effects, how they arise. We have a general sense of it in terms of physical theories, where to expect them. Quantum gravities are a totally different story. In fact, original attempts by Feynman to make sense out of it using the same techniques for field theories failed. So therefore, Feynman almost gave up. He says, well, we know gravity should be dynamical. We should be able to integrate. We should allow it to fluctuate. But when he did the same fluctuations that was working for gauge bundles and representations and so forth of matter, it didn't work when he put the metric fluctuations on the manifold. It didn't give sensible results. So he failed to make sense out of it. So string theory came up with potential examples, I would say, examples of cases where quantum gravity can be made sense out of. And the basic idea there was somehow in the context of quantum field theories, where we have the theory of particles, where you think about individual entities of fields as representing quantized particles, had to be replaced by strings. And so, for example, in this context where we talk about scattering of particles in terms of Feynman diagrams, here we talk about the two-dimensional objects, which we call the worksheet of strings. So you replace the graphs of lines and for particles with worksheets of Riemann surfaces, basically. So mathematically, this is nicer and smoother than this. And in particular, the graph is a singular manifold, whereas this is not a singular manifold. So you have replaced the 1D graph, which is singular in this case because of those vertices, to a 2D smooth object. So mathematically, this is smoother than that. And physically, it also ends up being better than that, and in the sense of it allows you to solve the problems of quantum gravity. So that's kind of a quick connection with what has happened in terms of decades of connection between string theory and quantum gravity, that this object is nicer than that. But we still don't understand deeply what this means and how restrictive this is. So for example, we have learned that the dimension of the space-time, so the dimension of the manifold in which we are describing the theory for quantum gravity seems to be, well, depending on whether we are doing the string theory version, well, let me do it first of all. The string theory version has to be exactly 10. This is bizarre because, you can not only, we don't need very mathematical sophistication to describe the Euclidean space in any dimension, but somehow this tells you, sorry, if you go anything above 10, we can't do anything with it. The theory breaks down, it doesn't make sense. That's peculiar. There's actually a slight correction here, which means that in some cases we have learned what it means actually for this theory to have 1 extra dimensions, or maybe even sometimes 2 extra dimensions, where some of the extra dimensions here is hidden in a form. But basically, the main point here is the dimension somehow seems to be bounded above in some fixed value. Very much different from quantum field theory. Well, quantum field theories, in fact, we thought that the only interesting ones are in 4 dimensions originally, like our space-time, or lower, but not higher. We have learned that's not true. We have learned, thanks to string theory, that there are interesting quantum field theories without gravity, without metric dynamically, which are interesting in dimensions all the way up to 6. We don't have any higher ones which are good, but up to 6, we have found good quantum field theory. Okay. So these kind of peculiarities, why is the dimension fixed, is great for physics. If we understood why, in a more deeper sense, why these kind of restrictions arise, this would give us a predictive power, because in physics, we want things to be very specific. We have one universe, we want to explain it. We are not living in an arbitrary manifold, an arbitrary dimension. No, we have a very specific one. If your theory makes sense in a very broad context, which might sound great mathematically, would not be great physically, because that would mean that you're going to be far from predictive power. If everything goes, then you can have no prediction. Okay, so we want to have something which says, no, not everything goes. In fact, very little goes. And therefore, you can have prediction power for our universe, which would be great. So that's the aim we are after, understanding why we are getting these peculiar restrictions in quantum gravity. Okay. I will just give you one example of these peculiarities. So when we say that the theory is in 10 dimensions, you could say, well, we live in 4 dimensions, 3 plus 1. So how is this compatible? So the way we describe this is that we take a Euclidean space with signature 3, 1, which is what we call Minkowski space, and you multiply it by an extra dimension, for example, a 6-dimensional manifold, to make up a total 10-dimensional space-time, and we take this space to be small. And so therefore, if this is small, you can kind of take an effective theory which looks 4-dimensional, and that's how we describe the usual physics, by having some what we call internal geometry, which is tiny, and that's how we deal with it. You might ask, okay, so what kind of theories do you get in 4 dimensions? Effective theory. So this can, in other words, you can get out of this some theory in 4 dimensions by doing some kind of intermediate what we call compactification. Compactification just means choice of this manifold in the middle here. So depending on that choice, you get some effective theory in 4D. What kind of things do you get? So there's a map between the choice of this M tilde and the choice of the 4D effective physics. 4D, what we call effective field theory. So there's a map from what you have to what you get. Okay, so let me ask, suppose we talk in 4 dimensions, you ask, what are the things that we want to get? Well, it turns out there's this property called supersymmetry, which is one of these beautiful symmetries in physics, nothing to do per se with string theory, but quantum field theories and string theory can have that symmetry. So let me talk about the maximally supersymmetric theory, because it simplifies life. Maximally supersymmetric theory in 4 dimension, which allows gauge groups, which allows gauge bundles, in other words, gauge fields. This is what we call in physics n equals to 4 supersymmetric theory. So suppose we ask this. What do we know about this class? Well, if you just ask about quantum field theory, this is characterized completely by choice of a gauge group. You choose a gauge group, you have defined the theory. It's unique. That's thanks to supersymmetry. With this much supersymmetry, just giving this defines the theory. You have a gauge bundle, you have certain fermions, you have certain scalars, which transform according to the adjoint representation of this gauge group, etc. And you can write a very specific interactions that's basically fixed. So quantum field theory is given by a gauge group. Any one of them is fine. And this theory is very beautiful. In fact, it's a finite theory. And it's what we call a conformal theory. So it's an example of a conformal field theory. It's a very simple, nice theory for any G. Now, let me contrast this with quantum gravity. So what does that mean? Well, quantum gravity in it has, in addition, the metric. Yes? Very good question. So when you talk about scattering amplitudes, so we talk about, in the physics context, gauge connections and so on give rise to particles. When you quantize, then you can talk about scattering of them. Basically, that means the formation of the gauge bundle, gauge connection. And so these scattering of these, which means the propagation of these perturbations of gauge connections, give you a probability of that happening, gives you what we call the amplitude. And we're saying those are finite. Now, in physical theories, typically what happens is that they are not finite, but what happens is a procedure called renormalization theory, which tells you if you redefine your theory appropriately, you can get rid of those infinities by connecting it to different scales that you might ask. So that zero length scale, things will be infinite, but finite length scale, they won't be. So this theory does not have that property, it's scale invariant. So that's conformal symmetry and so forth. So the conformal symmetry means even among the best theories, you don't have to work hard. It's just, there's none of these infinities. The scale dependence is not there. Things are much simpler. That's all. So it's among the best theories, simplest theories. Okay. So how do you get out of a quantum gravity quantum field theory? Well, this has a metric in addition. I told you that this theory has a dynamical metric. But it turns out there is a way to take a limit in this theory, which is what we call taking the Planck constant to infinity, Planck mass, sorry, not constant, Planck mass to infinity, which decouples gravity, which basically decouplers the metric, which projects this down to just the quantum field theory part. In other words, each quantum gravity has a reduction to a quantum field theory subspace. So there's a map from any consistent quantum gravity to the one which gets rid of the metric, just by taking this limit. So there's a map. Is that clear?
Exactly what? This is a map, the mass of what?
Okay, so there is the parameter in your theory, which we call the Planck mass. Now, what is Planck mass is what you might have heard in 4D physics as Newton's constant. So the Newton's constant is a parameter related to the parameter which defines the interaction of forces, basically getting that smaller and smaller, getting rid of it, basically. So get rid of gravity. So there's a limit where it gets rid of gravity, which decouples this piece, projects down to this subspace. This, as I said, this gives you this whole class. The question is this map onto or not? That's the first question. The big surprise is that not only this map is not onto, we think it measures 0 in the image. So this is what I'm trying to illustrate here. It could have been onto. In other words, if it was an onto map, means that any choice here is a way could come out from a completion, what we can couple it to metric with no problem. And it turns out that's not the case. That's far from truth. What we find is that the only possibilities are rank of the G to be less than 20, less than or equal to 22 for it to be coming. So in other words, you won't get all of them. The only ones you get from here have this, the image of this map leads to this restriction. In other words, it's measured 0 because for a generic G, you can have any rank. So you have now a finite set now. So suddenly out of an infinite possibilities, you now suddenly got only a finite number of them. That's remarkable. Very much against our intuition in physics. In physics, we would have thought, if this is so good, it's such a great theory, just putting some metric in it and allowing it to vary should not mess it up. The answer is that's not correct. It messes it totally up. Not as a classical equation, you can write classical equations, but making this metric fluctuating and all that messes it up and gives you such an amazing bound. So we think about the space of quantum field theories at this big space, and this consistent things like in string theory that you get will give you this projection map to the ones that are actually allowed. So the ones that I'm getting here is the one for which the rank of G is less than, in this case, less than or equal to 22. Compared to, of course, in that case, it's just the discrete points, but here I'm imagining these other parameters sometimes enter the theory. So out of as infinitely many possible positions you might end up, you end up with a measure 0 subset of it. And these points are what we call the landscape. That means the part of the theories that are good and the rest of it that actually are fine without gravity, without the metric, become bad. These we call the swampland. The rest of them are bad in this sense. They're not necessarily bad without gravity, but they become bad when you try to include gravity. Is that clear?
Could you give a little bit more details how we can prove? I mean,
I will tell you a little bit about it. We cannot prove it. So we can give evidence for why it's true. And first of all, in any context, there are two different kinds of paths you can take. Either using string theory. So string theory gives you construction, and then you could say, well, string theory gives you examples of this, but maybe there are other ones. So then we abstract from string theory examples, principles which are beyond string theory, hopefully, and then we try to use those principles to derive it. That's what we have done. But But some of those principles that we derive from string theory are also, you might ask, how do I know that principle is true? We cannot, in other words, some of those we cannot prove. Yes.
Will there be more specific restrictions, or is it just something like about the rank?
This is an example. In this particular case, there's also more. There's not every rank G less than 22 will work either. I'm just saying that's a restriction. But we can try to quantify what are the allowed ones and so forth. For example, SU23 gauge group is allowed and we can construct it. SU24 is not possible. It's just it's that simple. So that sounds bizarre mathematically. You guys say, what? This is crazy. How could you have such a structure? And I will try to say it's not crazy in a language that's more familiar to mathematicians. So let me explain why this is not surprising, should not be viewed as total surprise for mathematics. So, so I told you in order to go from here to here, we take m Planck to infinity or Newton's constant goes to 0. You're basically ignoring gravity. G Newton here, just not to confuse with the gauge group. But in order to get an effective four-dimensional theory, I told you needed an intermediate manifold, which we call the compactification manifold. We want to go down from 10 dimensions down to 4, so we have a 6-dimensional manifold. You could ask, what properties does this manifold have? Can it be non-compact? Even though I'm calling compactification, could it be a non-compact manifold? For example, could it be R6? Or some other things? Or does it have to be compact? It turns out compact versus non-compact is precisely this distinction. In other words, non-compact will land you to a case where G Newton goes to 0 in the 4D language. So you don't have a four-dimensional theory which is gravitational, whereas the compact ones with a finite volume ends up being related to this. In other words, there's a relation between this and the inverse volume of the manifold with some power. So in other words,
But when you say compact, this is bounded volume or it's really compact?
so physicists use the terminology compact in the sense of volume is finite. So either the volume is infinite or volume is finite. So the volume is, whenever the volume is infinite, you land into this class. When its volume is finite, you land into this class. Okay. Now, if you ask, okay, that's good. What are there any other restrictions? For example, it turns out in the particular class of examples I'm talking about, the class of examples you can have is hyperkähler manifolds are needed. And so it ends up being something like K3 cross T2 as the kind of examples that are allowed if you want to have a compact and a hyperkähler. And as you know, the homology of this is bounded. And it turns out this rank is not unrelated to the fact that the mid-homology of K3 is bounded. That's it. So you, of course, I know that that's bounded, so big deal. So that's not surprising mathematically, but then you remember that this mid-dimensional homology, which is the source of the gauge symmetries in physics, is related to possibility of a local behavior of a singularity, which is C2 mod the gamma, where the gamma is a subgroup of SU2. And there is you can choose cyclic subgroups or dihedral subgroups, and there are infinitely many choices, but not all of them can be embedded in a compact K3. If you choose an arbitrary Zn, for example, cyclic symmetry, that gives you SUN gauge symmetry for arbitrary n. So you can easily get arbitrary gauge groups from physics of this just by just choosing a local model here, which is not K3, but replace this by C2 mod Zn. For all n, it's perfectly fine. And this gives you an SUN gauge group for arbitrary n, no problem. But only a finite number of these n's come to a compact hyperkähler manifold. Not so shocking mathematically. Is that clear? So this is the version that is mathematically completely obvious, but physically this translates to this remarkable statement that what you thought is perfectly fine is not fine, and there's a very limited set of good things. Basically, compact versus non-compact structures. Is that clear? Okay. Now maybe I have over-trivialized it because, from math perspective, you say, come on, I know what compact, non-compact is. That it? That's the only difference. So that is a way to kind of get you to feel what is the issue at hand. But the point is that we are not given the intermediate space. We're just given what you see in lower dimension, and we want to see whether it's good or bad. And that's a hard problem. In other words, when you have so much symmetry, the maximal supersymmetry, which is everything is dictated by one group, things are much easier, and that's why we can say something. But when you reduce the structure, then it gets much more complicated. And the question is, if I'm only asking what on this side you're given and whether it's good or not, it's a much more difficult problem. We don't have a good handle. So the Swampland program is trying to come up with, yes?
Can you come back a bit? I mean, everything depends on the initial bound that the dimension has to be 10.
Yes.
Can you come back a little bit about that? Because you said that otherwise.
Yes, no, I mean, it comes, so in the supersymmetric case, which in this example was supersymmetric, you can easily prove the bound is 10 or 11 if you want to be more precise. That just follows by symmetry of supersymmetry. So in other words, in this case, we can also prove that. But you could also ask, what if I don't want supersymmetry, in which case I cannot tell you why it should be even bounded like that. Okay, right, so, okay, so here we are given this vast space of possibilities, which are only a few of them, or more precisely, a finite number of them we think are good in the sense that they could come from a consistent quantum gravity theory.
When you say finite, this is topological level or metric level?
So metric level. I think the talk that I think Matilda gave a talk yesterday. So for example, just to set the stage, if we think about the Calabi-Yau case, for example, just to be specific, gives you a certain amount of supersymmetry. We are saying that there are not only that there will be a finite number of Calabi-Yau, but their volume of the moduli space is bounded. So it's more than just the number. And the volume being bounded might require defining appropriately what do we mean by infinite distance in moduli space. So there is, I'll come back to that point. So we have a technical definition of what finiteness means. So I will tell you a little more about it if I get a chance. But the Swampland program is basically to try to come up with ways to identify, if I only give this space and tell you what is good or not, you have to give me a way to find out. It's hard to exactly find number of points in a measure, as a measure zero inside the space. How do we characterize this measure zero subspace? Extremely difficult. So we come up with kind of criteria. We say, well, it cannot be on this side of the universe. So we have some restrictions that we can say, these are principles that this property must hold, otherwise it's bad. So we can kind of narrow it down to some regions. This is not good, this is not good, this is not good, and then to basically limit the possibilities of what you could get. To exactly find it, it's very difficult, but you need to know everything about it, it's not easy. How do we know some of these exist? Is because we have constructions from string theory. So from string theory, we can come up with specific points. But if I'm not given string theory per se, which we don't want to use, we want to use more broader perspective, how do we come up with these criteria? Or if you already believe string theory is the only show in town, if it's the only possibility, you want to basically summarize what's executive lesson of what we have learned from string theory. What it is that will tell you is good finally, even in string theory, without going through the choice of the manifold or this and that. How do we characterize what is good? Okay. So this is Swampland program is precisely narrowing this as much as you want, as much as you can to basically, hopefully, only end up with these points ultimately, but that's going to be hard, but that's our aim.
But is there a nice formalization of the set of all QFTs? I mean, can you really put a structure of a space with
more? I mean, in the physics sense, we more or less understand, for example, in 4-dimension, what's the space of all QFTs. We can tell you what are the good ones and so forth. So that I think is not the main issue. It's not at the level that mathematicians would necessarily consider rigorous, but I think in physics, we feel we understand that. So that is, and we know, as I try to illustrate in this example, that's far from the actually good set that you can couple to gravity, that can come from this reduction from quantum gravity to quantum field theory.
But for instance, is there a notion of distance in this space of all QFTs?
When they have parameters, so when there are fields which are what we call the moduli, then yes, there's a natural parameter, and the way you define it, so in the physics jargon, the parameters correspond to fields, and so you have some actions, which is there's a metric in the moduli space, which I call Gij phi, which can be viewed as what is there in the action for the physics. So physics action comes up equipped with a metric on these spaces. So there's a natural distance, volume, everything.
But a priori, there are also infinitely many connected components.
Yeah, infinite, it could be, but a priori. A priori. But, and in quantum field theory, there is, but in quantum gravity, we believe it's finite. Yes.
Does these conjectures imply any conjectures about boundedness of Calabi?
Yes. In particular, the conjecture would lead to the statement that there are a finite number of Calabi. Yes. And
this rank bound is going from hyperkähler boundedness.
that was hyperkähler, in this case, transferred with the amount of supersymmetry. I told you I'm putting supersymmetry. That's equivalent to saying I will restrict to this class. If you reduce that, you reduce supersymmetry. So supersymmetry is a way to simplify our problem. Mathematically means put more structure on your manifold. So with no structure other than real manifold, then you're back to no supersymmetry. And then it's much more difficult to say something. But we can try to reduce the structure. Like the next class will be Calabi, the next class will be Calabi, higher dimensional Calabi, not threefold, and so on. So depending on what you put, or G2 holonomy manifolds is less than Calabi threefold, and so on. So it depends on what kind of structure you put, you can reduce that. So, of course, in physics, we are ultimately interested in no supersymmetry because the universe we live in does not have it, at least not in low energy. So we should not have it ultimately. So our aim is to get rid of it, the discussion. Somewhat like the discussion that you had about the algebraic subclasses, easier or more interesting, or we can say something more concrete about those classes. Supersymmetry plays that role in some sense. Okay. Okay, so now just to make clear that I'm not trying to say it's easy math. So let me try to characterize it. So you might say, oh, okay, so let's be very general. We start with 10 dimensions, but we want to go down to 4 dimensions by some intermediate manifold. And so what are the possible choices of the manifold? Let's say I don't put any structure other than possibly that you could write the effective theory in 10 dimensions on this manifold. Well, typically you have some kind of structure, like this is smooth manifold maybe, or maybe you want to have it spin manifold because you might have spinner on it, or if it's orientable or not, you have pin structure or not. So it depends on exactly what category you're in, you get different categories of objects that you can have. So the first order question is, what are the different types of theories you can have? What kind of different manifolds you can have? So that leads naturally to the notion of the Cobordism classes of manifolds that you can have, which are inequivalent. And typically you end up with non-trivial, for example, in this 6-dimensional case, of whatever category it is, you typically find that the Cobordism classes is typically not trivial. So you have different classes of examples. In math, you can have this manifold and that manifold cannot be connected smoothly and so forth. So there should be different classes. One of the big principles of quantum gravity is that this is always trivial. Always. And this is a big surprise for math. So that's what I want to say, that it's not the intuition of the math suddenly breaks down. Mathematical intuition says that's perfectly fine to have different classes. Physics of quantum gravity says, oops, you're missing something. It better trivialize ultimately. What that ends up being is that when you compute this and you find it's not zero, you are saying that because you're avoiding some singularities or something. It turns out there are very specific allowed singularities which kills those classes and trivializes it. And that is always the case in quantum gravity. So quantum gravity always finds a way to trivialize the Cobordism classes. So that already shows that we are going away from this study of smooth manifolds and so on. We have a bigger agenda here. And this is a manifestation of it. It's not as trivial mathematically as one might have thought. Okay, this is called the Cobordism conjecture. Again, we cannot prove it. Now, why do we know this is true?
Are you assuming M is allowed to have singularity or just the Cobordism between two of them?
Well, the class of, when you go through the family of Cobordism, but bounded singularity is the same question, right? But this is more than just that. It includes other objects because it's not just a manifold. You have bundles on it. You have, in addition, other structures that all of them together should have certain allowed singularities that are not obvious not everything goes, but something goes. And exactly which ones go, which lets it kill these, is not obvious what it is. But physics gives us a hint of what it is. Okay. Okay, so now you might ask why? How do we know possibly such a strong statement? Why does it trivialize? So I will give you again a physics motivation of why these principles we believe in. And it has to do with the big mysteries of black holes. So black holes are probably the most, it captures the imagination of people, of course. Black holes, these mysterious things, everything falls in, nothing gets out, and it's scary when you hear about them and so forth. But it actually turns out theoretically, they are the most interesting objects for quantum gravity. So theoretically, forget about all the hype that goes with it. It turns out they are most interesting objects for physics of quantum theory of when you try to make the metric fluctuate. And so what is that makes these are interesting? Is that, so I'll try to, first of all, motivate why these objects are very interesting physically. And then I will try to say, how does this relate, for example, to the Cobordism classes being trivial? So, suppose you want to, so how do physicists try to understand what is happening at short distances? So the way we do it in experiments is that we take particles, we collide them. And to bring the particles near each other, we need to go to higher and higher energies. So when you go to higher and higher energies, you can get to shorter and shorter distances for particles coming together and create new physics at higher energies. So basically, we are interested in increasing the energy of particles going in and getting more and more interesting stuff. So because high energy going up, means the distances that you're probing, you're probing short distances. So higher energies, because they're inverse relation between energy and distance scale you're probing. So if you want to probe what's happening at the ever shorter and smaller distance scales, you go on higher and higher energies. Good. That's what we are doing, for example, in Large Hadron Collider. You're getting things at the higher and higher energies. It turns out that, so you might say, well, am I going to get infinitesimal distances if you go to infinite energy, maybe? The answer is you don't have to work hard, it turns out. It turns out if the energy passes a certain threshold, things become easy. Easy, not hard. So there's a maximum complexity in this problem. This is already related to the maximality of difficulties. It turns out that if E is bigger than tank mass, which is what I was telling you before, answers of these we actually know. In fact, if E is much, much bigger than in Planck, we know the results of these scatterings. How could it be? Well, Large Hadron Collider is trying to get these energies. They're trying to get the energy of the order of 10 TeV, 100 TeV, whatever. So this scale is 10 to the 15, 16 times higher than that. I'm saying up to that, I don't know exactly what you'll get. But after that, I can tell you the life simplifies. It's not, the complexity does not grow with these kind of forces. We know how it happens. And the reason is, if these are high energies in a small region, it actually forms a black hole. Because the higher energy states at the short, small distances means that you have put a lot of energy into small region, and that's what defines a black hole. So you create a black hole. And the black hole, then what's the result of this scattering? It turns out that Hawking told us that the black hole slowly radiates away. So that means you know the result of this kind of scattering by using what Hawking taught us, using large distance physics. Not small distance physics, but fat, big black hole physics, which is easy to do. So in other words, it converts a problem which we thought is short distance to a problem which has nothing to do with short distance, but has to have a big fat black holes evaporating, and that can be calculated reliably. So this is already the beginning of the surprise of the black hole. Is that clear? So this is the physics of the problem. But what does it have to do with this kind of statement? Well, part of this has to do with the statement is that Hawking basically argued that black holes decay. They disappear, okay? Now, if you have some kind of non-trivial Cobordism classes, you can choose those classes and throw it into the black hole, but the black hole evaporation is universal, doesn't know about what you threw in, so it gets rid of that class. So the class should be trivialized by the process of being eaten up by the black hole. So in other words, So let's just give you a concrete example. If you take the spin manifold and you take a case of a spin cobordism classes as the fourth cobordism class of this is non-trivial, and K3 is representative of that class. The first Pontryagin class of it is non-trivial. So you say, aha, K3 is a non-trivial cobordism class for that. What do you do with it? So what you do is that if you have a four-dimensional space and a black hole in four-dimensional space, so this is a black hole, you take a K3 and glue it to the rest of the space like this. So you basically, what we call it, do a connected sum it to the rest of the R4 and bring it near the black hole and let it be eaten up by the black hole. And then black hole evaporates and K3 with it goes. The memory of the class does not come out because it turns out that Hawkins shows that the evaporation process is blind to what went in. It just depends on the total mass. Therefore, you lose the information about what went in. And therefore, it better be trivial. So this process gets rid of it. Yes?
Can you say a bit more? If you lose A, then it becomes trivial, but why was it already trivial?
Well, to us, the triviality means that there's a physical process which kills it. This is an example of it. So in other words, what you thought is a good class is not a good class. It's not an invariant. This is connected to nothing, which means the class disappears. Okay, so these are some aspects of how some of these, fancy math, well, cobordism is not very fancy, but at least the simple ideas that people can compute suddenly become surprisingly irrelevant or has to go away, but actually not quite, because from that we discovered there should be this process and we look for objects which trivialize it. Yes?
So I don't know if this can be explained on the same level, but what does this kind of thing have to do with, say, making these classes trivial by allowing certain singularities?
So this process of this going inside the black hole and evaporating, ultimately you get nothing left. That means it's trivialized the class. So that process is a cobordism path. Is the intermediate manifold, if you want. If you think about the time evolution, think about what is the cobordism. You have a manifold with one higher dimension whose boundary is this manifold. I'm just saying that you get this K3 here, and at the end there's nothing. K3 is gone. And that path you can view it as time axis, so that you have killed the class through this process. But the objects you ended up with may not be a smooth manifold, maybe some crazy thing. So what's happening there is that the category of what's happening is allowed because we know black hole is allowed. Therefore, from physics, we know it goes away.
But is this sort of thing specific enough to tell you what kind of singularities you should look at?
Not exactly, no. I'm just saying that this will tell you that there should be a refinement of what you mean by the category to kill that class. It's not going to be just a spin manifold. Or smooth spin manifold. There must be an extra category. What to do exactly at each step is not clear. You introduce this new object which kills K3, and then you might do the calculation again for the cobordism, and you might get a new class. And then that class should also be killed, and then you introduce new class. So in this case, you find new ideas, new objects that are needed. I'll give you a simpler example than K3. For example, so RPN, for example, for some of these N's are non-trivial cobordism classes, representatives of these classes. So if you take a RPN, it's just, Rn plus 1 over Z2 locally. That is a singular geometry. That object turns out to be allowed in string theory. So it kills these RPN classes. But you wouldn't have a priori known that should be a good object. Why should you have allowed the singular space like like the singularity which kills the RPN? That's okay, and that's known to be okay in string theory, but it's not obvious that should be good. I'm not saying every singularity is okay, but I'm saying we know certain cases like that is okay. Yes?
So, Cumrun, I'm not entirely sure why you, and also the audience, are necessarily talking about this as geometry, because this annihilation of the cobordism class is almost certainly going to involve non-perturbative quantum gravity effects, wormholes, whatever. And as a result, it's not at all clear to me that you can describe it in terms of a single geometry, right? You might need to inherently think about the wave function on all possible geometries and even non-geometries, and you might be going through that. So
yes, it is possible. It is possible for sure.
Right.
So,
right.
but let me say,
so while I agree with the conclusion for sure, right? it's really not clear to me that has a geometric description.
You're asking about what's the final space of it.
No,
I'm not, but sorry, let me just,
dynamic.
just 1 second. At large geometric sizes, like the example of RPN, explains a geometric object which is okay. That's an example of a geometry which I killed. That part of a geometry perfectly makes sense. You're asking, does it kill everything like geometry? That's a different question. Certain geometric objects will kill some of these cobordism classes, certain singularities, like the singularities that of Rn mod Z2 will kill the RPN. That's what we call orientifold in physics. Not a big deal. It is geometric. It is not, non-perturbative physics. It's nothing amazing. From physics, we say it's trivial. Just add it to your
Right,
allowed
that's
things.
not what's accounting for the dynamics inside the black hole.
No, it does. Well, in this case, it kills that RPN class. I'm just giving examples where cobordism gets.
Of the dynamical effect associated with quantum radiation or whatever that involves the RPN.
The example of K3 is far more complicated, that's for sure. I'm just giving you as an illustration that even that should go away. Even that should go away.
Right, it's a different thing.
It's not a different thing in the sense that you have to kill a cohomology class, cobordism class in that case. You're killing it. The process is harder. It might involve a non-geometric object, so I'm not disagreeing with your premise. But there are plenty of examples where geometric objects can be allowed to kill them too.
Yeah.
So to connect to my math audience here, I'm giving those examples.
Okay.
There are more exotic examples we can give, which is not geometric, but that's not my aim.
Fair enough.
So basically, we are trying to here understand what is this big theory, the theory which does this kind of things, which in some corners gives you things which we understand geometrically. That's part of the deal here. Now, I'll just give you one application that we just recently did with Kai, who's sitting right there, Kai Shu, and with Hichio Kim, just to give you an example of what kind of things we did, which is more concrete mathematically, so that you don't think it's all just some vague statements like this. So we asked, in physics jargon, we were interested not in 4D, but in 6-dimensional theories with minimal supersymmetry, which is what is called 1,0 supersymmetry. So we are looking at this class. Now, we were interested in trying to bound this class of what are this kind of class. If you take this space I was telling you, we wanted to know, can we bound the allowed choices if we assume 6-dimensional with 1,0 supersymmetry? Mathematically, these can be obtained in the constructions in string theory, and I think maybe, I don't know, Wadi will talk about it maybe tomorrow, I'm not sure. This turns out to be related to elliptic Calabi threefolds. So elliptic Calabi threefolds, any example of this would provide one of these points. Okay. To say that this class is finite would say that this class is finite. And thankfully, this is one of the cases that mathematicians have proven that's finite. So this is an example where we know the non-trivial topology types of elliptic Calabi threefolds are a finite set, and so therefore this is consistent with this picture. Okay, good. But we don't want to assume that this is coming from string theory. We don't want to assume there's anything to do with Calabi at all. We want to go from bottom up. We want to think about what are the consistency conditions of these theories. Can we deduce what are restrictions that would be for Calabi? Because if we do that, we put a restriction directly on Calabi as a sub-example, not as the only possibility. Is that clear? So if we had a way to find what are the conditions here, we could potentially put the restrictions on Calabi as a corollary of that statement. So that's basically what we did. We used some physical criteria in the 6-dimensional theory, motivated by these Swampland restrictions, to see whether or not we can bound this class. And we ended up being able to bound it. And we found, if you translate it to the language of elliptic Calabi threefolds, we found that the Hodge number of the elliptic Calabi threefolds, which should be less than or equal to 491. And this is actually great because this is saturated. There is a Calabi exactly with that, and that's the highest known one, thankfully, so it's not contradicting our statement. So this shows that there is no Calabi with a higher bound. So this is a physics argument going backwards up to bound the number of elliptic Calabi threefolds. And it gives you also a bound on the base, H1, the H11 of the base of this elliptic fibration, which shows that it's less than or equal to 194. So these are argued from physics side, building up backwards to what are the restrictions, but it's more general. It could have had that nothing to do with string theory. So it's quite refreshing that the bounds we get are precisely the ones that string theory would have provided you anyhow, potentially. And that means that the idea that string theory is the main game in town is reinforced. That is, even if you didn't assume it comes from geometry, it's giving you features which looks like geometry anyhow, regardless. So that means that this principle we call the string lamppost principle or string universality is that everything has a way to be described in some way using string theory, string geometry, or some generalization of it, perhaps with non-perturbative effects. So that's part of an example where we have a concrete math statement, which would be interesting. So there is a recent paper also by our math and physics colleagues where they put a rigorous bound from math side for elliptic Calabi-Yau, which is not as sharp as this one, but it gets closer to this bound. So at any rate, this is the physics kind of a argument.
Victor, so in this world of Calabi-Yaus, what would this Cobordism hypothesis predict, actually? Because
well, we don't restrict it just among the Calabi-Yau cobordisms, but one can in principle ask. I don't know what the answer for that is. Maybe somebody knows here. But so we usually do it for more general ones because Calabi-Yau is not necessarily the only one. The Calabi-Yaus are good if we want to have supersymmetry. But we don't put that condition a priori in physics other than to try to simplify our task of classifying it. So we are most interested in non-supersymmetric. I'm going to come to what challenge that will pose in a second. But let me say before I do that, yeah, maybe I'll go right there. So part of the so supersymmetry. What does supersymmetry do for us? Why am I saying supersymmetry so many times? It turns out that we believe, and this we don't have a proof of again, that this property we call supersymmetry is the only class which brings stable solutions in quantum gravity. So quantum gravity stability might require supersymmetry. So that's a much more fundamental statement. So let me explain what I mean by that. We believe this is the case. At least in physics, we have no counterexample to the statement that if you have a quantum gravity with no supersymmetry, it's unstable. That means it's not going to stay put. It's going to evolve in time. It's going to decay. It's going to have something. So supersymmetry is crucial to stabilize this problem for us. It's not just mathematical convenience. It actually has something to do with stability. Stability means stationarity with time. Things don't evolving. Now, we don't have a proof of this statement, but this is true in all the examples we know in string theory. Whenever we break supersymmetry, always there's some instability pops in. No example we know of which is not supersymmetric and stable, nice forever. That universe, which has that property, won't last forever. There will be some change. There's no stability in this situation. Now, how does this translate to a mathematical statement? So let me explain that's why, and that was related to my question to you when I was asking you. So we expect that this is related morally. So if we take these intermediate manifolds, I call them M6, you could have things, roughly speaking, flat. I'm being approximate with this, Ricci flat, scalar flat. Let me just be very vague here. Ricci flat, let's say, or negative or positive in the intermediate one. It turns out that these two classes are typically arise in string theory and are okay. And this class gives rise to these unstable ones. So the issue of positive or zero first Chern class is the stable category for us. And those negative ones are the ones which will always go away somehow or disappear. So it's a bad class in that context. So that differentiation is part of the key difference. And now we live in our universe in this situation, as I told you, and it seems like it's the analog of having a negative, if you were to put it in the manifold language, it's negative curvature, which gives you a what we call a positive cosmological constant, which leads to instabilities that we might be seeing in our universe. And that's one of the predictions that some of these ideas might lead to. But I think I'm running out of time, so let me just stop here. But I just hope that I gave a flavor because there are many conditions that I wanted to write down, but I think that would not have been very useful anyhow. So let me just stop here and open up to questions. Thank you.